Now we proceed to discussing the proof of the main theorem. Theorem 6 is very different from the theorems from previous lectures. Theorem 6 establishes the convergence of the objective values, which are the f of xk plus g of yk, and also establishes the convergence of constraint violations, which are matrix A times xk plus matrix B times yk minus vector c. Theorem 6 does not establish the convergence of the iterates. And the convergence proof we present below does not rely on the machinery of monotone operators. The main challenge of the proof is to construct an appropriate Lyapunov function, which is a name or term borrowed from nonlinear systems used to prove the system stability. The proof is not very long, it only takes about 4 pages in the textbook. It's relatively easy to follow. It's easy to verify. However, the construction of the Lyapunov function and some of the inequalities are not intuitive. This is because ADMM-type methods are modular. The classic ADMM is the simplest form. The proof comes from the insights that we have accumulated over the years of reading and writing papers on various different kinds of ADMM-type methods, from simple to more complicated ones. Let us define the constants and the Lyapunov function used in the proof. Recall we assume total duality, which means the Lagrangian L has a saddle point x star, y star, u star, and concatenate them into vector w star, and also concatenate the iterates xk, yk, uk into wk. Define a constant eta, and define 3 block diagonal matrices. The off-diagonal entries are all 0, and the assumed conditions of the theorem guarantee that the matrices on the diagonal are all positive semi-definite. Therefore, we can use them to induce semi-norms. And define the Lyapunov function as wk minus w star norm induced by m0 squared plus wk minus 1 norm induced by matrix M1 squared, and we will use matrix M2 later. To clarify, this norm is the sum of the norm between x star and xk induced by half time p, and the norm of y star minus yk induced by half times this matrix, plus the norm of u star minus uk induced by this matrix with half in front of it. So there are really 3 terms here and another 3 terms there. Using these concatenations and the block diagonal matrices allow us to write the proof and the Lyapunov function in a concise way. At this stage, these choices don't explain by themselves. They actually come out of the proof. Let's start the proof. We will present the overall flow of the proof in 4 stages, and we discuss what to achieve in each of the 4 stages. However, in the lecture, we will not explain how to obtain every inequality, so for you to verify or to understand the whole proof, you must read those 4 pages in the book. The proof begins with the fact that xk plus 1 and yk plus 1 are subproblem minimizers. Using the optimality conditions of subproblem minimizers, we can write out 2 inequalities, one that relates xk plus 1 to x star, and the other relates yk plus 1 to y star. The one relates xk plus 1 to x star will involve functions f1 and f2, matrix A and matrix P, similar for the other one. Adding the 2 inequalities and use definitions of Lagrangian L and definition of update uk plus 1, you can write down this inequality where the left-hand side is non-negative due to the definition of Lagrange, and the right-hand side includes 4 squared terms and 2 inner product terms. To clarify, the first inner product term is induced by the diagonal matrix M0. So that really it expands into 3 individual inner product terms, one involving x vectors, and the second one is involving the y vectors, the last one involving the u vectors. Recall from previous lectures that in the proofs we always come up with non-negative terms to draw conclusions on. However, given the information so far, we're not able to determine the size of these 2 inequality terms yet. Therefore, we need to further transform and decompose them. We first bound the second inner product on the last slide. Notice that there are yk plus 1 and yk in this inner product. So we can use the fact that yk and yk plus 1 are the y subproblem minimizers at the k minus 1th and the kth iterations. And they give 2 inequalities, and add those 2 inequalities, we can obtain this new inequality, where the left-hand side is inner product, and the right-hand side is its bound. And this bound involves 3 quadratic terms, including 1 negative quadratic term, as well as 2 new inner products. At this point, we simply apply Young's inequality to relax these inner products. And Young's inequality states that the inner product of 2 vectors A and B can be bounded by their individual norms with proper weights. Here, these weights involve a scalar zeta that is any number positive. If zeta is taken as 1, then this reduces to the Cauchy-Schwarz inequality. When you apply Young's inequality to a Q matrix induced inner product, you simply get on the right hand side the Q matrix induced norms. And when you apply it with the negative sign in front of the inner product, you still get the same right hand side because the right hand side is always non-negative. When we apply this Young's inequality to these 2 inner products, and we choose different zetas for these 2 terms. Apply Young's inequality to the 2 new inner product terms on the right hand side, allow us to get the new right hand side. And we have used this induced norm notation to collect the terms. So we end up having only 3 terms, one involving yk plus 1 minus yk, the second yk minus 1, and the last one uk minus 1. The second term is non-negative because the matrix is positive semi-definite. The last term is also non-negative. However, the first term is undecided because it's unclear whether this matrix is positive semi-definite or not. If it is negative definite and yk plus 1 is different from yk, then this term is actually negative. We write it like this only to save space. There are other yk plus 1 minus yk norm terms with different matrix, and they're going to combine, all of them going to combine. We only need to ensure that the matrix as induced norm for yk plus 1 minus yk in the Lyapunov function to be positive semi-definite. So we were applying Young's inequality to the 2 new inner product terms on the last slide. You may wonder, what if we directly apply Young's inequality to this left-hand side term rather than taking 2 slides to taking these steps to get this bound? Well, if you do that, then we will not able to obtain terms of yk minus 1 and this term. So these 2 terms will not be obtainable. And this will not allow us to include these terms in the case Lyapunov function. And which also means any yk plus 1 minus yk terms have to be absorbed not by the Lyapunov function, but by another means, which we will not able to do. Recall in stage 1, we ended up getting 2 inner product terms to handle. In stage 2, we have bounded the second inner product term, and this is the remaining inner product term, and it can be handled by this generalized cosine identity. So add this identity, the bound from stage 2 to the bound in stage 1, we end up getting this master descent inequality, which states that the case plus 1's Lyapunov term is less than or equal to the case Lyapunov term subtract this amount. So this is the amount that the Lyapunov function has to decrease minimally at the case iteration. This term is non-negative because M2 is block diagonal and positive semi-definite, and we have argued that this Lagrangian difference term is also non-negative. Recall that the Lyapunov function formulation involved two squared terms involving two positive semi-definite matrices. So the Lyapunov function is lower bounded by 0. It's always non-negative. So this descent inequality immediately means that this term have to converge to 0 as k goes to infinity, as well as this term. So applying the summability argument on the master inequality tells us these two conclusions. The wk plus 1 minus wk norm term converges to 0, and this one decomposes to 3 induced norms, and the last one is the induced norm of uk plus 1 minus uk. So it actually tells you uk plus 1 minus uk converges to 0. And looking at the formula for uk plus 1, this is just a scaled version of the constraint violation. So the constraint violation must also converge to 0. Looking at the second conclusion, and we expand the first Lagrangian term to f and g evaluated at their respective points plus this inner product. And this one is equal to f of x star plus g of y star plus 0, because in the inner product term, the constraint violation is actually 0 because everything's optimal. So this difference converge to 0 really means f of xk plus g of yk converge to the optimal objective. So these are the two conclusions we have in the theorem. Next, we're going to derive several ADMM-type methods by customizing FLIP-ADMM. Apply theorem 6 of FLIP-ADMM to these methods. We're going to obtain the range of parameters to ensure their convergence. Let's first look at a class of linearized methods. The word linearization refers to more than one technique, but most often it refers to canceling out inconvenient quadratic terms and leaving with linear terms and super simple quadratic terms like the 2 norm of x squared. Set f2 and g2 equal to 0 for simplicity, and look at this standard ADMM formulation. Applying ADMM method to this formulation will ask you to solve subproblems where the x subproblem involve a times x plus constant 2 norm squared, and the y subproblem will also have b times y inside a norm squared. Therefore, a and b can cause difficult subproblems. With these choices of p and q, we can recover the linearized ADMM method, which we have seen in chapter 3, except there we don't have the dual extrapolation parameter phi. In the linearized ADMM method, we no longer have ax inside a square. Instead, we explicitly compute a times xk and a transpose times a precomputed vector. and only F is involved in minimization, not A times X, and similar for Y. And this method is called Linearized ADMM with golden ratio parameter. So you can call it golden ratio linearized ADMM. According to theorem 6, this method converges if alpha times rho times the maximum eigenvalue of A transpose A is no more than 1, similar for beta, and rho is strictly less than, phi is strictly less than the golden ratio. The primal dual hypergradient method of PDHG is a special case of linearized ADMM. Consider this formulation where we have set A matrix to negative identity. So we can substitute X by b times Y. So the original objective is simply F1 of by plus G1 of Y without explicit constraints. To obtain PDHG, we can set phi equals 1, phi equal to 0 matrix, and Q like this in linearized ADMM on the last slide, and apply Moreau identity to deal with proximal of F1 star instead of proximal of F. And this way obtain the formulation, which is known as PDHG. Linearization can also mean linearize a function. In FLIP-ADMM, the access to functions f2 and g2, which are differentiable, are through their linearizations. So the subproblem only uses their gradients as the recent iterates. And this feature, we have argued, provides great flexibility. Let's use this feature to recover the Cadet-Wu method. Consider this formulation where we have also include g2 of y as a differentiable function besides g1. Apply FLIP-ADMM with rho phi equals 1, p equal to 0 matrix, and this Q matrix. Give us this formula and apply Moreau identity to deal with proximal F1 star instead of proximal of F1. We obtain this two-step more compact form of the same iteration. And compared to PDHG, the only additional term in this new iteration is this term which involves gradient G2. Applying theorem 1 will obtain this condition that guarantees convergence. However, it's worth mentioning that this condition is worse than the condition we obtained in chapter 3 using a different method. Cadet and Wu did not consider the second differentiable function f2 besides g2. So here we include f2 and g2 and also put a matrix back. We apply FLIP-ADMM, which is going to linearize function f2 and g2, and also use P and Q matrix to linearize the quadratic term involving ax and by. So we get this formulation where we access f2 through its gradient, g2 through its gradient, and avoid minimizing ax by. So we access A and A transpose by matrix vector multiplication, similar for B. And we also include this dual extrapolation constant. So we call this method doubly linearized ADMM, which stands for linearizing both the access to the functions, to the smooth functions, and the avoiding the awkward quadratic terms ax and by. So this method generalizes PDHG and Cadet-Wu, and we'll list the convergence conditions here. Next, let's introduce a technique that we call partial linearization. Consider this formulation where we have dropped F1s simply because we want to give a more concise presentation. Assume rho A transpose A or gamma times identity plus rho A transpose A is difficult to invert. However, there exists a matrix C that's close to but different from rho A transpose A, and this matrix is easy to invert. And under this assumption, we can choose a P matrix, which is gamma identity plus C minus rho A transpose A, and choose a gamma such that this P matrix is positive definite. Because these two matrices are similar, so gamma can be pretty small. Then applying FLIP-ADMM with this matrix P, we get this X update, in which we access the gradient of F2, we access A and A transpose, multiplying a vector, and invert this matrix that's easy to invert. So this step is easy to compute. This is what we call partial linearization, and this can also be applied to the Y problem. Compared to full linearization, to cancel out A transpose A in the quadratic using this P, or cancel out B transpose B using a Q matrix that we saw in the previous two slides, this iteration reduces the total, this update reduces the total flip iterations because gamma is relatively small and we are inverting something that's close, essentially close to what we want to invert originally. Let's demonstrate the power of partial linearization using CT or computerized tomography imaging with total variation regularization. Let X represent a two-dimensional, three-dimensional image that we're going to recover from CT measurements B. The B may contain noise or artifacts. And we minimize the loss function. We assume this loss function is CCP and of AX minus B. So to keep AX close to B, where A represents, A is a discrete Radon transform which approximates the physics of CT imaging. We also add a regularization term, that's total variation. We write it down as the one norm of over D of X, where D is finite differencing operator. We can apply PDHG to this formulation. However, it has too many iterations, although every step is cheap. Classic ADMM requires much fewer iterations than PDHG. However, it has very expensive step because we have to invert this matrix. Now, since A transpose A and D transpose D are discretizations of shift invariant continuous operators, they can be well approximated by circular matrices. So we use a circular matrix C to approximate this sum. This A transpose A and D transpose D are not themselves circular matrices, at least due to boundary conditions. They're not have circular boundary conditions. Let's explain why this matrix is easy to invert. For the moment, let's assume the CT image we deal with is only one-dimensional and has n entries. In this case, C is going to be n by n. And let little c transpose be the first row of capital C, and little c hat be the discrete Fourier transform of little c, and let F be a discrete Fourier transform. By the convolution theorem, for any vector x, we can multiply this matrix so x can be computed by first computing the inverse Fourier transform of x, multiplied to this diagonal matrix, which is equivalent to component-wise multiply x brief with this vector. So this costs On, and then apply this Fourier transform. And fast Fourier transform only costs n log n. So while in general this calculation can cost n squared, the calculator on the right-hand side only costs n log n. Now, the same can be said about multiplying this inverse matrix to x. It's equivalent to multiplying x brief by the component-wise inverse of this vector, followed by a Fourier transform, which altogether costs n log n. Whereas in general, if you first compute this inverse matrix, then multiply by x, the first step, computing the inverse itself, can cost n cubed. So we say calculating or multiplying this inverse matrix to a vector, to any vector, is easy by fast Fourier transform. FLIP-ADMM with this matrix choice of matrix P implements partial linearization, and you end up getting this formulation where we have used model identity to deal with prox of L star. And in this formulation, in this iteration, we use this inverse, and this is the only matrix inverse we need. And we don't compute this inverse, we use Fourier transform or fast Fourier transform to implement this line. So they have easy to calculate steps. The first step involves multiplying matrix A to a vector followed by proximal of L star. And the second one, multiply a matrix D to a vector and followed by a projection to a box constraint. And this method converges under this condition, which follows from theorem 6. And compared to classic ADMM, there's only a minimal increase in the total number of iterations. And compared to PDHG, the total iteration is much smaller. And compared to classic ADMM, the cost of every step is significantly reduced from a cost which is probably n cubed to a cost only n log n. Next, we're going to present two splitting techniques for a class of problem that we call multi-block ADMM problem. Partition a p-dimensional vector into m non-overlapping blocks of subvectors. The I subvector has size pi. The sum of p1 through pm equals p. Similarly, partition a matrix into a block of columns in this form such that A times X is the sum of each block times the corresponding subvector. So we write a multi-block ADMM problem in this form. It is also called extended monotropic program. There are m functions, each with their own variables xi, and then all the xi's are combined or coupled together by the constraints. Unless all the column blocks are mutually orthogonal, that is, each take the i's block transpose times j's block equals 0, that is, all the columns in the i's blocks are orthogonal to any of the columns in the j's blocks, and vice versa. The blocks, when you update these blocks in ADMM, you cannot update them independently because they couple together in the quadratic term. So we're going to present two splitting techniques so they can indeed update independently in parallel. The first technique is what we call Jacobi ADMM. In numerical linear algebra, the Jacobi method is an iterative method for solving certain linear systems, where all the blocks of X can be updated independently. To achieve similar feature in ADMM, for the monotropic program on the last slide, we introduce a matrix P in this form. All the diagonals are gamma times identity. The off diagonals are minus rho. The i's block transpose times the j's block that form the ij's block of this matrix P. We ensure P be positive semi-definite by requiring gamma greater or equal to rho times the lambda max, the maximum eigenvalue of A transpose A. Define the Lagrangian as the original objective function plus the dual variable transpose inner product with the constraint violation as well as rho times the penalty of the constraint violation. Let X sub inequality sign I denote all the components of the vector excluding the i's block. Then FLIP-ADMM with that matrix P, remove all the function G, set G to 0, Q to 0, matrix B to 0. Will give you this formulation in which the X update automatically breaks into m parallel updates, whereas the i's block xi k plus 1 is a result of argmin of this Lagrangian which uses the case version of all the other blocks. And this method is called Jacobi ADMM, drawing its analogy to the Jacobi method for linear system of equations. So P here serves the role of linearization, and this linearization decouples the column blocks of A. We refer you to exercise 8.3 for other choice of P and the conditions of convergence. The second technique we introduced to obtain independent xi updates is called dummy variable technique. And this technique can be applied to slightly more general problem. The form has an additional function g of y, where g is CCP. If g is indicator function of the origin, then it forces y to 0, and this formulation is equivalent to problem 5. To decouple zi's to get independent updates of xi's, we introduce dummy variables z1 through zm, so that every zi is equivalent to an ith block of A multiplied by xi. So in the constraints, all the AI blocks are independent, all the zi's are independent. However, the i's are coupled in the objective, where c minus the sum is equal to y. We have eliminated y. Apply FLIP-ADMM with matrix P equal to 0, matrix Q equal to 0, no function linearization, and set the initial value of u variables to consensus. Then we can show this method will keep all the components of u equal forever. Therefore, instead of writing so many different u's, we just use a single u. And then this way, the iteration will simplify to this form, where xk plus 1 can update all its components in parallel, independent of one another. And then they use uk, the xk, which are the last iterates of all the components, as well as the sum of zk. We do not need to keep track of individual zi's. And the sum of zk can be updated this way, where we have involved g. And this method converges if phi lies between 0 and the golden ratio. Next, let's re-examine the consensus technique and see how it plays with FLIP-ADMM. Consider this finite sum problem where we minimize f of I of x, sum over I equals 1 through n. Using the consensus technique, we can introduce a variable z and let z equal to xi. Here xi is a copy of x, and making this copy in order to get easy subproblems. And this is different from what we had in the last few slides, where xi represents a subvector or a block of x. Apply FLIP-ADMM with these choice of matrices, no function linearization, and an initial u variables satisfy their sum equal to 0 to get this update. Because xi's in the formulation is no longer directly related, they are related indirectly through the z variable. Therefore, using the last copy, fixed and last copy of z variable, the x subproblems decouple. It decouples to an independent problem where each of them involves fi, ui, and the common zk. After all these copies of x are updated, then you update zk, which is their average. And finally updates the dual variable ui, one for each of xi. This method converges if rho is between 0 and the golden ratio. The consensus technique is very versatile. Instead of assigning xi equal to the single z here, we can also equal them to different copies of z variables where they are connected through a graph. And that will allow us to obtain not only a parallel method, but a decentralized method in a later chapter, chapter 11. 212 ADMM is a technique that increases the number of blocks that an ADMM method can be applied to, assuming the additional blocks are strongly convex quadratic blocks. Consider a two-block ADMM type of problem where we have f of x plus g of y, and assume that g function is a strongly convex quadratic function with optional affine constraints. That is, g can be written in this form where m is symmetric, strictly positive definite, so this part is strongly convex quadratic, and it's possible to include linear constraints. And if so, nu have to be in the range space of n such that this constraint is feasible. We can ignore that, we can exclude the constraint if it doesn't exist. Define the standard augmented Lagrangian of this problem with f and g, a and b. 212 ADMM refers to the method where we first update the second block, then the first block, then the second block before a dual update. So in every iteration, the second block is updated first, update the last, and sandwich the first block update. Otherwise, the formulation is very similar to ADMM. When you update every block, you always use the latest version of other variables. It turns out this update, when G is strongly convex with an optional linear constraints, is equivalent to a single block FLIP-ADMM applied with this choice of P matrix. That is, we minimize the augmented Lagrangian with this P matrix induced norm, and we're minimizing over x and y jointly, and then followed by the dual update. So because x and y are updated together, they're not independent, and this is a single block, although they have two subblocks of variables. And this method converges if rho is chosen between, if phi is chosen between 0 and 2. And this idea can be generalized to deal with 4-block ADMM, where 2 of the 4 blocks are strongly convex blocks with optional linear constraints. And that 4-block ADMM problem can be solved with 2, 1, 2, 4, 3, 4 sequence of updates. And there are 2 exercises that describe these methods, as well as its generalization to include function linearization and proximal terms. The last method of this lecture is triple ADMM. It is short for triple linearized ADMM. It applies to this generalization where we have inserted matrix C in F1 of X and inserted matrix D in front of Y. F1 and G1 may not be differentiable, so this is not a trivial generalization. In trip ADMM, it accesses F2 and G2 through their gradients, and it avoids inverting anything involving A or A transpose, or C or C transpose. However, we pay the price of taking 3 steps to update X and taking 3 steps to update Y. In every iteration, matrix A is multiplied only once. A transpose after combining terms is also multiplied only once. So is C and C transpose. Gradients are also accessed only once. So despite of these more statements, more steps, the cost is not increased much. And triple ADMM generalized FLIP-ADMM. So it also generalized doubly linearized ADMM. It generalized linearized ADMM, which further generalizes Kandet-Wu and PDHG. Under these parameter conditions and under total duality, define these C tilde and D tilde matrices. Then we have objective convergence and constraint convergence. Specifically, we have constraint converges to 0, constraint violation converges to 0. What I did not write here is that this two additional terms that involving C tilde transpose C tilde and D tilde transpose D tilde, these two terms themselves will converge to 0. And therefore, this quantity inside F1 actually converges to C times xk. And this quantity inside G1 converges to D times yk. So this will be the objective sequence, and this objective sequence converges to the optimal objective sequence. Finally, let's conclude this chapter by summarizing FLIP-ADMM. FLIP-ADMM is a combination of 4 techniques: oscillating update, method of multipliers, the linearization technique, which refers to 2 kinds of linearization. One applies to quadratic terms, the other applies to function linearization through access to their gradients. And the last technique, the use of proximal terms, which can implement even partial linearization. And these techniques can be combined like modules in any way to solve problems of very complicated structures. In addition, other techniques such as dummy variable technique, consensus technique, Jacobi ADMM technique can help us solve problems with even more blocks. ADMM type of methods you see in this chapter are splitting methods. They're related to monotone operator methods which split operators. However, ADMM methods often split blocks. They're intimately related, but they're not monotone operator methods themselves. So for the general FLIP-ADMM, especially with dual extrapolation parameter phi, cannot be reduced to a monotone operator splitting method. Therefore, they must be analyzed directly, like we did in Theorem 6